Welcome to my clips on the analysis of statically determinate frame. The frame shown here is a steel frame. This steel frame is fabricated by connecting the beam to the column with the rigid joists. And this frame also has support. One can be pinned, another one can be lower and pinned. If one is pinned and another is lower, this frame is called statically determinate. Can you draw the model of this frame and apply the force into this frame? Yeah, usually if this is a pin, you just make this is like a pin, and then you attach this pin into the support. Okay, and then this for statically determinate frame, you model this one as the roller. Okay, and support to the floor here. And for this column, okay, it can be up like this, and along this you can draw the lines of the horizontal line, and then on this you may draw the column. And since this is the rigid joist, okay, you may put some fixed rigid connection into here, and also needs to be here. Okay, and this frame may subjected to what? This frame may subjected to uniformly distributed load. Due to what? Due to the weight of the beam itself. And then following this, you draw the weight here, and then it's going to be the model that can use to analyze the frame. And if the weight of here is maybe a lot, you may put some more rod over here, and sorry for this, you just put the line along here. So this is the model of the frame. When you draw it, this line gonna represent the centroid of this beam, this column, and centroid of the beam is going to be the straight line. And next, another rigid frame. This rigid frame, if you take a look, the support here can be the pin support, okay, and also over here can be the pin support. And what happened is the weight of this small beam can transfer to what? To this beam. So this one going to have the reaction here, and also this one going to have the reaction here, and the reaction here going to put to the girder. Sorry, let me put another color, so it's going to put, it's better. So take this one out, and then let you select the pin with another color. Okay, let's see this one. So the selection here will apply into this beam, also will apply into this beam, and this beam also subjected to what? This beam may be also subjected to its uniformly distributed load along its length, and this one also subjected to uniformly distributed load along its length. And then this uniformly distributed load gonna be the reaction here, support by the reaction here, and also support by the reaction here. And by the third law of Newton, okay, the reaction here may apply again to the beam of the frame. Okay, and also this frame have its own weight. So this frame gonna have what? It's gonna have the uniformly distributed load along its length. Okay, like this, and you can see the model of analysis of this frame can be created easily, and then all the forces will transfer to the support, to this support. Okay, and you may see this one, and since this support are pinned, this structure is statically indeterminate. Okay, unless you assume one of these supports is the roller. Again, you may see on this frame the load will transfer to the cross beam here to be the reaction. Okay, and that reaction is transferred to act on the girder. Okay, and the girder have its own weight. They transfer all the forces into the reaction. Okay, the yellow one, and this reaction by third law of Newton change to the green force. And since the beam of the frame have its own weight, is also apply the force across the column and from the column to the support here. This is a kind of the model that we use to model the frame and for the analysis of the frame. Okay, and we come to a simple structure here. The frame here is assumed over here. Since the frame over here is a steel frame which have the column here and the beam here, and the F is the free end, so the support E must be fixed support. Okay, under the action of the force, we can analyze it first by draw the free body diagram of the frame, and then we have what? We change the fixed support into the reaction, and at the support here they are supposed to have 3 reactions to make the frame be in equilibrium. Summation of f sub x equal to 0, summation of f sub y equal to 0, and summation of the moment equal to 0. And then if you like to draw the shear diagram and moment diagram of the frame, after you know these forces, for example, this one gonna be summation of x sub x equal to 0. This one gonna be 0 kilonewton. And then if you do the summation of f sub y equal to 0, you will get what? This one going to be the vertical force going to be equal to 1,500. Again, by using this frame, if you take the moment about this point, you may see that the moment is going to be equal to what? Equal to 1,500, and it's going to time the distance between here and here, which is going to be what? 4, 5, and then this is going to be 6.5, and then the moment that we are looking for is going to be 6.5 and time 1,500. That is going to be the moment going to be 9,000. Okay, 700 and 50. Sorry, it's not kilonewton, it's 50 newton and meter. This is going to be 0 newton. Okay, that's going to be the frame reaction. And then if you like to find the internal forces and internal moment to draw the shear diagram and moment diagram, you got to set, for example, this one gonna be the coordinate one. You may call this is like a x1 or y1, whatever you set, and this is going to be another x2. And then if you cut the beam, sorry, the frame into the given section, you can write the shear force in the function of x1 and x2, and also the bending moment at the function of x1 and x2. By that case, you will get the equation, and then you can draw the shear diagram and the moment diagram of the frame. Okay, by doing this, we go further. Most of the frame, let me know, the frame may have the column subjected to only axial load. That's we call the column. And if the frame subjected to both axial load and bending moment, we call this frame as the beam column. Okay, it is important because the combination of moment and P may produce the P delta effects. Okay, when you study the design of this member, Ajahn will tell you about the code that related only to the column and the code that related to the beam column, which is much more complicated, and therefore sometimes we need to draw the axial force diagram also to include the effect of this into our analysis results. Okay, and let us do some example so it will enhance your understanding on the drawing of the shear diagram and moment diagram. Let us consider the first example, which is the frame. This frame have the A as the pin and has the D support as the roller. So if that happen, we will have the force A sub x and force A sub y as A, and has the reaction force only in the vertical direction at the D. So we will have three unknown forces, which is equal to the three equation of equilibrium. So we can solve it. By doing that, we will draw the free body diagram, and then we will use the equation of equilibrium. By doing that, we take the frame out of the support, and then we put the reaction in according to the support. At D, we have D sub y because it is roller, and at A, we have the A sub y and A sub x because it is a pin. So we start by summation of f sub A equal to 0. And you can see if you put this, the A as the rotation, so the D sub A trying to rotate like this counterclockwise. So if you say like that, you may say if that we will have the summation of the moment at A equal to 0. Okay, and then since this rotation is for the unknown, so we set the rotation like this is positive, and then our D sub y going to multiply by the moment arm between the D sub y and the rotation point. That is going to be 5. So we have over here is 5 D sub y, and then the uniformly distributed load here, they're gonna have the resultants of it in this direction, and you may see the volume of this is going to be what? The magnitude of this is going to be the total of 16. It's going to be 16 kilonewton per meter, and then it's going to have what? The length of it is 5 meter. So it's going to be what? 16 times 5. It's going to be 80, right? 80 Newton. And then this 80 Newton will have the line of action along here. And you may see that it's going to be half of the 2.5. And then it's going to produce the moment in this direction. So it's have minus, and then 80. And then it's going to have what? Time 5 divided by 2. Okay, next we come to another load that acts on the column. On this, it's going to also have the resultant force here. This resultant force is going to be what? The area of the force is 12 times what? Times 4. That is going to be what? 48. The total here is going to be 48 kilonewton. and then the distance between this resultant force and the rotation point is going to be here. That is going to be what? That is going to be 2 meters, and also it's going to rotate like this, so it's going to be minus, and then 48 what? 48 times 2. Okay, and you may set this equal to 0, and you do the computation, you will get the d sub y of 49.2. Okay, then you may have the summation of f sub y equal to 0 in order to determine the a sub y. The a sub y is upward. Let's take the upward as the positive. So we have the a sub y, and then the a sub y will plus both vertical plus 59.2. Okay, and the resultant force of 16 kilonewton per meter have the downward. Okay, have the downward. When it have the downward, so that is going to be minus of what? Minus of the 80. When it's minus of 80, it's going to be what? The a sub y gonna be 80 minus 59.2. So the a sub y, okay, that is gonna be 80, and then going to be minus 59.2. So you're going to get what? It's going to be 20. This one going to be 20.8 kilo Newton. So you got the a sub y here for 20.8 kilonewton. And then the last one is here. Okay, we have the summation of f sub x, and then is equal to 0 to determine a sub x. So we put this direction as the positive. So our a sub x is positive, and then the uniformly distributed load on the segment AB gonna take the what? Opposite direction. So a sub x is going to be 48 kilonewton. Okay, and then all the forces are going to be in equilibrium. And after we determine the reaction, next step we're going to separate the frame into 3 parts. Okay, into 3 parts: 1 part, 2 part, and 3 part. And we put the reaction that we have into the support at A and at D. Now, the problem is, what is going to be the shear force and going to be the bending moment acting on the end of this member? When you cut this, don't forget about the joint here B and joint here C. Okay, because it's part of the structural member. And then what happened is, if you consider the column CD, you may see that this column has what? Has only the vertical force. So there is no horizontal shear here. Shear here is supposed to be 0 because there is no horizontal force. And also the moment here also needs to be 0 because there is only the axial force along the member. So we have only the force here. So this is like said to be C sub y. And if you do the summation of f sub y equal to 0, you may see that your C sub y is downward. It's going to be positive. So C sub y is going to be 59.2 kilonewton. So you get this green, okay, in the same direction, and then this is 59.2. This 59.2 going to act. Okay, let me change this one a little bit to the green yellow. So light green here, yeah. And then the force over here, due to the third law of Newton, when this 59 is downward, so the force X over here must be upward. And due to the equilibrium of this point C, the force here must be downward with 59.2. And again, due to the third law of Newton, the force here also must be vertical. And then for summation of f sub y equal to 0, you may see this one is going to be 59.2. Okay. Okay. Now let us consider the NB. Okay. The B is going to be the rigid joint. So if this happen, okay, we going to have the shear force here, and the shear force going to be like this. Okay, this is going to be V sub B. Okay, and we also have the vertical force. Sure, we're going to have vertical force, and we also need to have the moment. And if you do the summation of x sub x equal to 0, this horizontal force is going to be 0, since there is no horizontal force here. Okay, and by doing this, if you summation of f sub y equal to 0, by doing this, you will get what? The v sub b is upward, so the upward is going to be positive. You're going to have v sub b. Okay, your v sub b is going to be upward, and then 59.2 also plus. Okay, 59.2, and then if you remember the resultant force of this uniformly distributed load, if you remember, what is the value of this? The value of this is going to be 16 times 5, so the value of this is going to be 80 kilo Newton, and this is a downward, so minus, this is minus 80, and then equal to 0. So all the vertical force is written here, and then you're going to have V sub B equal to what? 20.8 kilo Newton, and this is going to be 20.8. Okay, 8 kilo Newton. And then if you sum the summation of the moment here, you may have this one for the m sub b. Let's see, if you do the summation of moment above b, and then equal to 0, you may get m sub b. Let m sub b rotate like this. Okay, m sub b rotates like this. Okay, let me have this one already is 20.8, and oh, sorry, this is in opposite direction. Let me try to erase this a little bit. This is not good. Okay, this is not good. Okay, this is going to be m sub b. Let's say, let's put this in this way. This is going to be m sub b. So we have summation of moment above b. So the counterclockwise is going to be plus, and then we have what? We have m sub b equal to 59.2 times this length. This is going to be 5, so it's going to be m sub b. And then 59.2 is in opposite direction, minus 59.2 and times the length of 5. And then we have the resultant force of 80 kilonewton, which act at the half of 5 meters. So this is going to be in this direction. This is going to be in this direction. So this is going to be plus what? Plus 80. And then 80 times what? 80 going to times 2.5. Okay, and then make it equal to 0. And then you put into your calculator minus 59.2 times 5, and then this is minus, okay, 80, and then you get, this is not a good lighting. Okay, this is better, and this 80 is not good. So make it good, better than here. Let me draw it again. By using mouse, it's pretty hard to write it in a proper, beautiful manner. Okay, and then we have this. Then we do the calculation. The m sub b gonna be 96. Let's put other thing in the calculator and check it out before you go further. And then the obtained shear and moment gonna be what? The moment here gonna transfer to this one by the third law of Newton. The upward shear gonna be downward shear. Okay, and the downward shear going to be this axial force, and this one going to be 20.8 kilonewton, transferring from this blue to this red up this one, and then is apply vertically. Sorry, apply vertically here. So it's going to be downward. Okay, downward here. Okay, over here, and then the moment this clockwise be this counterclockwise, and then for the equilibrium there is a moment here in which is going to be the moment at here. So we have the moment here, and then if you do the summation, you may see the summation of the force in the vertical direction is equal to 0, and then if you do the summation of F sub x sub x equal to 0, you may have this force, which is, if you remember, is 48, okay, kilonewton, is going to balance by this force. Okay, this is going to be correct. If you do the summation of F sub y equal to 0, you may get 20.8 and 20.8. And if you like to do summation of the moment about what, if you like, about b, and if it's equal to 0, if you have this one is 96, rotate this one is plus, is going to be 96. And if you do this, you have what? You have this one going to rotate in the same manner of this green moment. So it's going to be 48 times what? 48 times 2. This is plus. Okay, plus. It's going to be 48. And then times 2. And then what? You have this 48. Okay, this 48 going to be rotated in this way. So it's minus. This is another 48, and then it's times 4. Okay, and you may see this is going to be equal to 0. So this equation is also correct. So everything is in equilibrium. If everything is in equilibrium, now we draw the shear diagram and moment diagram. We first take the column AB as our first piece. When you draw the shear diagram of the column, it's going to be from the A to the B. That means what? That means you got to put the x equal to 0 here, and then up here is going to be 4 meters. Up here is going to be 4 meters, and it starts from the bottom to the top. So when you move to this, you got what? You got the horizontal force. So this one is going to be positive 48, and then you come over here, the slope dv by dx is going to be minus 12. So by doing this, the slope here is going to be equal to minus 12. Okay, that's really bad drawing. Sorry on that. Okay, let me take this one out. So we made it a lot better. So this one going to be minus and also 12. And then what is going to be here? Okay, if you take a look here, there is no shear, so this one's supposed to be 0. Okay, if you won't believe it, you may have the shear here, the shear at B, V sub B, and then minus what? Minus 48, minus the 48, and it's going to be equal to what? Equal to minus the area here. The area here is going to be 12 times 4. And then you can see clearly V sub B is equal to 0 kilonewton. Okay, that's proof. And then for the moment, there is no moment at A. So the moment at A start here is going to be 0, and this is going to be 4 meters. Okay, and the moment here start by 0. However, we have the shear here. So when it start here, the dv by dx, the slope here, gonna have some value. Okay, this gonna have the slope here, the slope here. Just start the slope here. The slope here must be equal to this 48 because dm by dx equal to v. Okay, up until this we have the s slope equal to 48. Okay, it's put here, and then also the shear change from 48 to 0. So that means at the end of this is going to be slope of 0. So over here is going to have slope of 0. So we have here s equal to 0. And what the value of the moment here? And if you can predict, this is going to be 96. But if you don't believe it, we can do it m sub b minus m sub b is here minus the moment here of 0, and then it's going to be equal to the area sorry, the area oops, misdrawing, the area of, let's put this way, it's going to be better highlight. Okay, the area of this. So the area of this is going to be 1/2 of what? 1/2 of 48. 1/2 of 48 equal to 1/2 of 48, and then time what? Time the length of 4, and then you may see m sub b gonna be what? Gonna be 48 times 4 divided by 2. That's going to be 96 kilonewton and meter. Okay, you get this already. Next, take a look at the beam BC. Take a look at the beam BC. From this, we have slope of this of 48. This is slope equal to 0, and then you take this of 96. Next, take a look at the beam BC. For the beam BC, again, we draw the shear diagram, and then we start with the B. The B has a shear of 20.8. Okay, up to this one, and then you move up, you get the distributed force of 16. So dv by dx, which is the slope, is going to be minus 16. Okay, and then this is going to be moved downward like this, and then the shear here, you may not believe it, it's going to be v sub c is equal to v sub c. V sub c is here. Oh, not equal to v sub c minus takes minus of what? Minus of 20.8. Minus of 20.8. This is going to be 20.8, and then it's going to be equal to the minus of the area here. If you see, this is going to be 16 times 5, which know to be 80. So your v sub c is going to be minus 80, and then you plus 20.8, and then you get the 50 minus 59.2 here. And since this is 59.2, you have what? You have the upward. So this one gonna cross your shear diagram here. Okay. And the distance here, can you find it? Okay, the distance here, maybe let's say it's going to be 20.8 divided by what? Divided by x. That's it's going to be 20.8, and then you divide it by x. So it's going to be what? It's going to be the slope 16. So if you move x up, this one going to be 20.8, and then it's going to divide it by 16, and then you're going to get this of 1.3 meter. Okay, you get everything. That is going to be your shear diagram. How about the moment diagram? And then you come to this moment. The moment that's rotated clockwise is positive. So this is going to be up for 96 kilonewton meter. And then this is going to be the slope, dm by dx equal to v. So the slope here, the slope at this point. Okay, you may mark this one is s equal to 20.8. this one is positive, right? Okay, it's positive. And then over here the shear is 0, so the S at some point of this gonna be 0. And what the value of moment here? Value of moment here must be M, and then minus what? Minus 96. When n minus 96 is going to equal to the area here. Okay, the area here is what? The area is 1/2 of 1.3, and then it's going to time what? 20.8. Okay, 20.8. So you will get the value here, or by what? By M. Then it's going to be equal to minus 96 is going to be plus 96 here, and then it's going to plus what? It's not what? This is going to be 10.4. 20.8 divided by 2 is 10.4, and times 1.3 is 13.52. This one is going to be 13.52. Okay, and then you plus 96, it's going to be 109.52. So the result of this is going to be 109.52. Okay, over here show only 149.5. okay, kilo Newton meter. That is the moment here, and the slope here is also must be 0, and you have the curve here. And finally, since this C section have no moment, so for sure this is going to be 0. And then you got to provide the slope as this important point. The slope here is going to be what? The slope here is going to be equal to shear, and since shear is minus 59, so slope here is going to be minus 59.2. You may see every point have their own lesson, what the value they are. Okay, and finally we have the column ACD, and this column have only axial force, so the shear is 0 and the moment is 0. And that is for the first example for drawing the shear diagram and the moment diagram of the frame. And then you combine the whole picture of this, and when you combine it, you must provide the value of some important point, and then you put the slope. Okay, the slope for here is going to be what? Memory is so sleepy. Sorry. The slope here is what? The slope here is gonna be, if you may remember, to be what? Sorry, it's gonna be minus 12. Okay, that's going to be minus 12. So the slope here, just put the slope to be your example. S equal to minus 12. Okay, and you may highlight to make it a little bit more understandable. Okay, this is highlight, and this is highlight, and to make this more clear, this highlight. Okay, and then you also has the slope of this. This also have the slope. Okay, the slope, and have the slope. The slope of this is going to be minus 16 if you remember it, because the uniformly distributed load here is 16 kilonewton per meter, so this is going to be minus 16. Okay, and the column here is okay. And then again, for this is going to have the slope of 20.8, and this is going to have slope of 0, and this is going to have a slope of 59.2. and if you may like, you may put this one, the slope here is okay, equal to 20.8 at 20.8, and this one S equal to 0, and this one S equal to 59. Sorry, that's it hard. I got to buy some pen for this. Okay, this is going to be minus 59.2. And then for the column, okay, we have what? We have the slope here. The slope here is going to be equal to this. This is 0, so slope here is 0, and slope here is what? Slope here is going to be 48. If you second. Okay, you just say this S is gonna be 48. Okay, and this S is gonna be 0. Okay, and that is your your conclusion of the shear diagram and moment diagram. And then you get the maximum moment of 109.5 on the beam and get the maximum shear of 48 kilonewton for the column there. Okay, that is the end of our first chapter. Sorry, our first example on the drawing of shear and moment diagram of the frame. Okay, this clip again will be the example of the analysis of statically determinate frame. And after we draw the free body diagram, we find the reactions, and then we will draw the shear diagram and bending moment diagram by using the graphical method. Coming into this frame, let's consider the support by this figure. This support is the roller, okay, due to the construction of this, and the support at A is going to be the fixed support, and what we have also is the joist here. This is the pinned joist. Okay, when the joist like this, we're going to separate the beam, and then it's going to help us to analyze the structure. The fixed support has what? Has 3 unknown, and the roller supports have 1 unknown. That means what? We have unknown of 4, which is larger than the number of equilibrium. If we consider the whole structure, we cannot solve for the reaction of 4. And what we do again, since this connection is the hinge support, or is a kind of support that cannot take the moment. So when we separate the column AB to the beam BC, okay, again, this is will be 4. We cannot solve it. We need to separate into beam and column. So when we separate this, what we have unknowns is 4, so we will be here, and at the B we could have B sub X and B sub Y. Okay, the B sub X is the blue, and this is going to be B sub X, and the pink, and then the vertical is going to be B sub Y. Let's say it's B sub Y. And when you have this kind of connection force by the third law of Newton, you will have the blue in the vertical direction. You may notice this. What? This is the shear here can transfer the here directly, and also the normal force here will transfer to this directly. Or if you are so detailed in calculation, you may consider the joist here as the B joint, and then you may transfer the axial force here first, and then the shear here, okay, by the third law of Newton. This is to the left, this is to the right, this is up, this is down. You also get this axial force due to this shear force, and you will get this shear, okay, to be this shear. And you can see, you may do detailed calculation by putting the column, but you also can skip this, and you can transfer it directly in the condition that there is no force and no moment acting at that joint. If there is moment, or if there is force, we cannot transfer this directly. Okay, let us consider this. And then the force here can be separated into vertical. When it's separated into vertical, the 3 gonna times 100 and then divided by 5. And for the horizontal, this 4 will be divided by 5 and then times the 100. Okay, it's up to what you are going to project to. If you project vertical, you use the vertical divided by 5. If you project horizontal, you use the horizontal length divided by 5. And now, if you like, you may determine the forces. Okay, about here. By determining the forces, we start by taking the moment about B, summation. Moment of B equal to 0. And then the C sub y gonna rotate like this. Have the clockwise, counterclockwise rotate is positive. So we have C sub y. Our C sub y gonna time what? Our C sub y gonna time the total of 6. Okay. And then the beam usually assume have very small depth. So the inclined force will produce very small moment and negligible. So it's only on the 60 times 5, this is going to be the 60 kilonewton. The 60 kilonewton gonna rotate what? Gonna rotate in the clockwise direction. So when this one rotate in clockwise direction, so it's in opposite to this. So it's going to equal to what? 60. 60 is a force here, and it's gonna time what? It will time 6. Okay, and then this is 60 times 6. So the C is what happened? No, this is not times 6. This is going to time 3. Oh man, what happened? This is going to time 3, not 6. Because the distance between the distance between the force and the B sub B is going to be here. That is going to be 3. Okay, and then the C sub y gonna equal to what? 30. Okay, 30 kilonewton. And then you get the C sub y of 30 kilonewton. And then you get this. You go further to determine the force. What you can find? Summation of what? Of F sub y equal to 0. You can determine what? You can determine B sub y. Okay, so this is up is positive. Okay, so our B sub y is up 30 is up. Okay, all of them is going to be equal to the downward of 60, and then the B sub y is going to be 30, and it's understandable because the 60 kilonewton is at the middle of the beam, so it will transfer half to the left and transfer half to the right. So each of them get 60 kilonewton. And then the last one, use summation of f sub x equal to 0. That means at this time the b sub x over here is, let's say, is plus. So the b sub x is going to be what? The b sub x is going to be, this one is going to be 80. This is 80. So this is going to be 80 kilonewton. And you will get this is 80 kilonewton. Okay. And this is 30. This is 80. And 30 and 80 can transfer to here. The 80 is here. Is follow this. And also the 30 is here. And now the portion of this, the unknown, that's total of 5, now is reduced to only 3 unknown. Okay. And if you like, you may see summation of f sub y and is equal to 0, and you may see what? See the positive is plus, up is plus, and then you get the a sub y, and then the a sub y gonna be equal to 30 kilonewton. So the a sub y is 30 kilonewton. Okay, upward equal to the downward. Okay, and then if you do the f sub x, okay, this side, if you do the f sub x equal to 0, and then what you have is the a sub x, so you put this at the positive, and then your a sub x is what? A sub x point to the left, and the at point to the right, and also the resultant force here also point to the right, so it's going to be minus 80. Okay, and also minus what? Minus the take is out, elastic. Okay, let's put it in again. It's going to be minus of what? The next is going to be 5 and then time 4. Okay, and you're going to get this equal to 0, and then your a sub x is going to be 100, right? This is going to be 100 kilo Newton. This 80, this is 100, and then m sub a. Then you determine m sub a. You got to take the moment here. You got to summation of m sub a, and then equal to 0. And what you have is rotate like this is positive. Okay. So by doing this, the m sub a is in this direction, and it's going to opposite to this repulsion force of 20 kilonewton. This is 20 kilonewton. 20 kilonewton gonna time what? Gonna time this distance, and this distance is 2 meter. So the m sub a is equal to, or if not equal to, okay, 20, and then it's gonna time 2, and then there is the 80 is going to rotate in this direction opposite to m sub a, so it's going to be equal to the 80. The 80. Oh, my hand is hard to control the mouse. So it's 80 times what? Time is 4. Okay, this is 4. And then this is going to be 330. This is going to be 40. So this is supposed to be 360 kilonewton meter. Okay, that is the moment m sub a. Okay, follow this. You have this 20 kilonewton. You have this 400 kilonewton, and you have this for the 30, and m sub a. M sub a is 360, as we have before here. Okay, we start by drawing the shear diagram. The first one is the beam BC. For the beam BC, we may have this one as the horizontal, and you may have this 30. This is the pass 30, and then what? No uniformness here, so the S. The S here gonna be 0. So the S here gonna be 0. And then you arrive here, you're going to get the 60. So this is 30. So it's going to be downward with this, or the 60. So it's minus 60. And then it's plus with 30. And then you get the result of minus 30. Okay. And then what? No uniformly distributed load. The S is equal to 0. And what we have is this one is constant. And then over here, you get this one for the 30. So that is going to be the shape of the shear diagram. And then the moment diagram. Oh, I supposed to buy the pen, if I should be. This is the pen, and then we have this as the horizontal line, and then what we have is 0 moment here, and also 0 moment here due to no moment. And then this is the 30. So the slope here supposed to be S equal to 30, and it's going to be all 30, okay, until here. And the moment here is what? You don't know it. The moment m is here is going to be minus 0, and it's going to equal what? It's going to equal to the area of this, and the area of this is going to be 30 times 3. So this is going to be 30 and then times 3. So what we have is the m here is going to be 90 kilonewton and meter. So you have this here, and then the shear change from the plus 30 to minus 30. That means we will have the S here equal to minus 30. Okay, and then also the moment here is 0. So you just draw a line cross to here. So this is going to be the triangle shape of the 90. Okay, and for the column, you have this, and then you start with what? You start with the shear diagram. You draw this line. Okay, and line is not vertical. take this one out, okay. Let's take this, okay. Take this one out, okay. We are like here, and then what? And you start to draw from 0 meter to here is 4 meter, and then we have what? We have the 100 Newton. So this one is up, and it's up for 100. Okay, this is up, and then it's up for 100 Newton. And then what? The slope here is going to be -5. So we have the slope along here is going to be -5. When slope -5, this one will have the straight line about here. It's really hard to draw this, so sorry for this. Let me erase all of this. Okay, and then just put the figure onto it, so it's going to be easier to do so. It takes it out. The mouse is not accurate to draw this picture here, so we have it. But it's going to be easier. Okay, the this one gonna have the value of what? 100. Okay, you like it's 100, and then you get what? You get uniformly distributed load. So the S here along this line, or the S, or the S, or this S, or this S is going to be negative. It's going to be a negative of what? It's going to be the negative of, my mouse pad is bad. This is going to be a negative of minus, this is -5. Okay, and see, you have the 80 here, so this is going to move this. That means the value of the shear here supposed to be 80. And if you guys won't believe that's one going to be 80, you guys can compute to check it easily. This is going to be V sub B. Okay, this V sub B is minus what? This 100. Okay, and then it's going to be what? It's going to be equal to minus of the area here. The area here is going to be what? It's going to be 20. So it's going to be -20. And then if you move this one, the V sub B is going to be -20, and then it's going to plus 100, and then you get this for the 80. And when you get this for the 80, the pink force just close the loop. This. Okay, next we have the shear diagram like this. Why this is in this direction? Because the clockwise is positive, counterclockwise is negative, so the moment here is negative. And then what? And you get this 5 kilonewton meter, and the m by the x equal to slope, and slope is 5. Sorry, so it's 100. This is 100. The slope is going to be 100. So this one is equal to 100. So the slope will change until here. And see, there is no moment here. So moment here is 0. And slope here is what? You got to put the slope here. The slope here is going to be 80. Okay, that is going to be the 80. So the shape of the shear diagram and moment diagram going to be like this. And finally, if you combine them, you got this. And don't forget what indicate the slope. This is going to be 0. This is going to be 0. Okay, and this is going to be -5. Okay, and then put some remark on this. It's going to help to indicate the slope clearer. So just mark this to highlight it. And this is 0, this is 0, this is 0, and this is 0. So it's going to be very clear how it's come. Okay, and also you have the slope here of 100 and slope here of 80, and then you have the slope here, and slope here of 30, and -30, -30, and -30. And if you can show your link, okay, you may see the 100, the shear gonna be the slope here, and also the shear gonna be slope here. You can say is S equal to 80. Okay, this is S is going to equal to 100. Okay, this is S is equal to 30. This is S is equal to 30, and this is S is going to equal to minus 30. Okay, that is the shear diagram and moment diagram. When you do the examination, you're supposed to put every important point with the slope and the related value. Okay, we are working on the new example on the analysis of statically determinate frame. This frame is a kind of steel frame having 4 members. If you recall the example that we have, I have the example with 2 pieces of the beam and column, and we also have the frame with 2 columns and 1 beam, and this beam has the 2 beams and 2 columns, and 1 beam BC is going to be the cantilever beam, okay, and attached to the joint at D, and has the column A support the joint D, and the beam DE connected to the column BE with the rigid connection again. By the shape like this, you may consider the support A as the roller, and support B by this figure is the pin. So we will draw the whole frame's free body diagram, and then we will compute for the 3 reaction by using 3 equations of equilibrium. And then we separate the beam into 4 pieces, and we analyze the end shear force and end moment, and finally we draw the shear diagram and moment diagram by using graphical method. Okay, the free body diagram of the frame, we have this, we have the roller at A, we have the pin at B, so we have 3 unknown forces. The best way is tying to summation of the moment about B and then equal to 0. What we have is we take moment here. So the A sub y has the line of action here. The distance from here to here is going to be 8 meters. And A sub y gonna rotate clockwise. So the rotate clockwise is set to be positive, and it's going to be 8 times what? Times A sub y. Okay, that is unknown. Gonna go by the sign, positive sign convention here. And then we have a lot of forces. The 6 kilonewton gonna rotate in opposite direction. The 10 kilonewton also, and this has the resultant also rotate in opposite direction. And you can see this is 7, this is 0.4, so the resultant is going to be 7 times 0.4. How many it is? It's going to be what? 2.8, right? Kilonewton. And then this distance going to be what? Going to be half of 7. It's going to be 3.5. So it's going to be 8 times A sub y, and then minus what? 2.8 minus 2.8 and 2.8 times what? Times 3.5. Okay, that's the first term. The 15 kilonewton produce no moment because the 15 kilonewton will cut the B. Okay, and then we have what? We have the 10. The 10 gonna go by the A sub y, so the 10 gonna times 8, so it's have minus 10, and 10 gonna times 8. Okay, and then we have the 6. Okay, 6 is gonna time the whole distance from here to here is 6, from here to here is 8, so it's gonna time 14. And then all of this is going to be 0. You put them into your calculation, you get this a sub y to 21.725. Okay, and next you go by the summation of f sub y equal to 0. By summation f sub y equals b sub y is up, so positive is up. We have the b sub y and b sub y plus 21 plus 21.725, and it's going to be minus 6 and minus 10, and then it's going to be what, b sub y plus this one minus 15 also, and it's going to be equal to 0. So this one is going to be 10, 25, 31 minus 21.725, that is going to be 9.278. Okay, and the last one we have summation of f sub x equal to 0, and you have what, you have the b sub x in this direction, put it as positive, so you got this one as b sub x, and you have the resultant here was what, 2.8, so you got this equal to 2.8 kilo Newton. Okay, it's going to be 2.8, and then you finish finding the reaction. You separate the frame into 4. Sorry. Okay, actually 3 is okay because the CDE is a hanging beam, can be. And don't forget the E. This time we need to consider, let me note this time, we need to consider the joint. Let me put it into the more light color to point this. We need to consider this because this time the joints have the 15 kilonewton. Whenever you have the joint with the force, you cannot neglect it. But if you go to the previous example, you may see the force can transfer from the end of the column to the end of the beam directly. That is because there is no forces and moment at the joints. Whenever it has, so you cannot neglect it. Okay, and then we put the reaction that we have into the segment or the part of the frame. And then if we start over here, okay, we have the force over here. The force over here, we just summation of f sub y equal to 0. You will get this force equal to this, and there is no shear, no moment, since there are only 2 forces here. This is a 2 force member per se, and then this force is going to transfer to act at the point D. Okay, and what, the E going to have 3 force: normal force, shear force, and moment. So we skip to this part, and when you know this, you're going to have the axial force. And what is axial force going to be? The axial force by summation of f sub y equal to 0, and then you get this one of 9.275. And for this one, if you summation of x sub x equal to 0, you get this equal to the resultant force of this, which is going to be, if you remember, 7 times 0.4, that is going to be 2 point, what, no, this is going to be 2.8 kilonewton. And if you summation of x sub x equal to 0, the b sub x and this one gonna eliminate each other, so the force here gonna be 0. Okay, and the last one we can compute for the moment, okay, by summation of the moment about this point, about point E, and then this is gonna be 0. Before that, let me take a note on this. So this guy is going to be what, 9.2275 and kilonewton. Okay, and this is going to be 0. And the moment when you take the moment at point E over here, you will get what? You will get the 2.8 this direction. The 2.8 is going to be in this direction. However, this one going to be in this direction. So the m sub e will plus what? Plus 2.8 times this one 3.5 plus 2.8, and then this one time 3 point and then 5 and go together. And the opposite direction you got a 2.8 also, but it's going to times 7, it's going to be minus 2.8 and times 7. This one going to be equal to 0, and then you may get the m sub e by putting in your calculator. You may stop the video and try to do so. What do you get? Okay, you may have this 0 kilonewton. This is 9.275. And what is m sub e you get? This is going to be 9.8. Okay, if this is going to be 9.8, it's going to be 9.8 here. That 9.275 is going to get upward. Okay, and then the shear is 0. And then what happened? This 9.275, this one is upward. Okay, this one is downward. So we need to have this one, okay, to make it in balance. So the shear here, the summation of f sub what, sub y equal to 0. The shear at the E, the shear is upward. It's got a plus 9.275 plus 9.27 and 5, and then this up is going to be equal to the 15. Okay, you do the computation. This is 9.275 and this is going to be the blue one. That is going to be 5.725. The 15 minus 9.275. So this is going to be my V sub E. Okay, it's going to be this. How the moment? The moment 9.8 here going to be this one going to be 9.8 also. So the moment here is going to be 9.8 kilonewton, and the 9.84 going to be this one. Okay, and the blue is going to be this one. So we have 9.8 and this is 5.729 and that is 9.8 kilonewton. And then up until here, so you have the reaction here, you have the internal force here. So now you are ready to draw the shear diagram, moment diagram of every member. So let's start this one first. So this one will have this, and you may see the 9 kilonewton gonna put this one down, and then there is no distributed force. This is going to be constant, and this one gonna take up, but you have 10 here, so it's going to up for 11.725. Okay, and then it's going to constant here and close here, so the shape will be down and up. Okay, so the shape will be like this. So the down is going to be like this, upward, downward, due to this 6 kilonewton. No distributed force. This is going to be 0. This is going to be minus 6. And the green and the black going to be deduct each other. That is going to be up for 11.725. So this is going to be minus 6 plus 11.725. And then we got this for 5.725. And then there is no distributed force, so the S over here is going to be 0. And then this is going to be plus 5.725. And then you get this downward shear. So this is going to be the downward. Take the downward move here, and it's going to cause the shear diagram again. And then for the moment diagram, you may see on the left the moment gonna be 0. However, on the right, you're going to have the moment of 9.8 kilonewton meter. So the moment diagram, since this end has no moment, so start here with 0. And then since the shear here is minus 6, so the slope here S is going to be minus 6. And then what's going to be here is going to be M minus 0. M this minus 0 is going to be equal to the area here. That means it's going to be equal to minus 6, and then it's going to times 6. Okay, and then the M here is going to be minus 36 kilonewton meter. Okay, and next the slope going to be here, the dv by dx. So the slope change from minus 6 to plus 5.725. Okay, and what is going to be the value of moment here? The M here is going to be M sub E. The M sub E here gonna minus 36 minus of the minus 36. Okay, and then it's going to equal to what? It's going to equal to the area here. Okay, you may highlight the area here. The area here is going to be what? The area here is going to be 5.725, and then it's gonna time, this is time 8, equal to 5.725, and then it's gonna time the length of 8. So the M sub E, sorry for very unbeautiful drawing. The M sub E, gonna be here. It's going to be what? Going to be here. Oh, okay, I lost my calculator. It's okay. It's going to be 5.725 times S, and this one is minus and plus, and then it's moved to the right. It's going to be minus. So this one is going to be 9.80 kilonewton meter. And then you get what? You get the 9.8 here, in which it is what? Counterclockwise. And it's going to be negative. When it's negative, that means it's going to close this one down, downward, okay, to close this end. So that is the moment diagram of this beam CDE. And then for the column BE, okay, we project this, and should we have what? This is going to have the 2.8 due to what? Due to this B sub x. And then we have the slope of S equal to minus 0.4. Okay, so the graph here is supposed to be like this. And since the shear is 0, since the shear is 0 here, this is 0, that is going to be 2.8 and is negative. Okay, negative. And then the slope here, this is negative 2.8. Slope here is going to be what? No, it's going to be plus. Okay, because the force is from the left to the right is negative. So this one is for the right to the left. It's going to be positive. This taking care of the uniform load, the direction. If you consider the column with the uniform load from the left to the right, okay, that slope is negative. And from the right to the left, that slope is positive. So this is 0. And then for the moment diagram, we have the moment here for the 0. And then we have this one as the negative. So the slope here, the slope here must be negative of 2.8. And then it's going to be reduced by the value of the shear, and then the slope somewhere here is going to be 0 slope. Okay, the slope here is going to be 0. And the moment here is supposed to be 9.8, and it's going to be minus because it's on the right, on this side. Okay, from over here 0, and then slope is negative, so this one is going to be minus 9.8 kilonewton meter, and the curve going to be like this one. Okay, and then we have 9.8 what? Clockwise, and then it's going to be positive. Okay, it's going to be like this, and close the loop here. Okay, and the small column is you go back and taking care of the column. This column, there is no shear diagram, and there is no moment diagram. It only has the axial force diagram. So we only draw the shear diagram for the beam CDE, okay, and the shear and moment diagram from the column BE. And okay, this is an example of a frame with 2 columns and 1 beam, and this frame has the pin at A. Sorry, this frame has the pin at A and also has the pin at D. So what it means is this frame, if you draw the whole free body diagram, you will have 4 unknown, and is larger than the number of equations of 3, so we cannot solve it. Anyway, if you consider it, this frame has the hinge connection at C. So that means we will separate the frame into A, B, C, and another one for C, D. And then we have the total of 6 unknown which is equal to the number of equation of equilibrium 3 plus 3. That is 6 equal to 6. This frame is statically determinate frame. Okay, and by separating the frame like that, let's say this has the a sub x and a sub y. This has the c sub x and c sub y, and you supposed to check that the force c sub x and c sub y here, they has equal magnitude, but in opposite directions, due to it follow the third law of Newton. Okay, and then over here we have the d sub x and d sub y. So we have a lot of unknown. How we will start our calculation? Okay, it's better to follow this step. Let's see if we take the moment, okay, at what? At the A, we take moment here, we will have an equation upon c sub x and c sub y. Okay, and then if you take the moment at the D, you also has the moment of c sub x and c sub y. Okay, if you do that, if you try to do so, you may some moment at what? At A, and then that's one gonna be equal to 0. If you do that, you got to set up the positive direction. If you set this one is positive direction, the c sub y gonna time the what? C sub y has the moment arm of what? Yes, the moment arm of this. Okay, this is the line of c sub y. This is going to be 8 meter. This is going to be total of 8 meters. So you have the c sub y, and your c sub y is going to time 8. So you have 8. Okay, and c sub y. And what else do you have? This is 36. 3 times 12 is 36. It has the rotation this in opposite direction, and also the 15 going to have the opposite direction. The 15 going to time by 4, so minus. Okay, and then 15, and then time 4. Okay, and then the 36 gonna have the 12.3, and it's going to act at this length of 6 meters. So you are going to have minus 36, and then time 6. Okay, and then you still have c sub y, in which c sub y has this moment arm. Okay, and c sub y gonna rotate like this. So you got to have minus what? C sub y gonna time the whole of this is going to be 12. So c sub x, okay, gonna time 12 meter, and then you got this one as equal to 0 for your first equation, and you can rearrange it. You may have this one for 8 c sub y minus 12 c sub x equal to this term. Okay, you can do it by yourself. And then after you take moment at D, again this one, sorry, I forgot to put this. Okay, you have the summation of the moment of what? Of point D. So we have this one of the point D, and then that is equal to 0. What we have is this one, the c sub y produce no moment. Okay, you have only c sub x, in which it act like this. So counterclockwise by the c sub x is positive. So the c sub x gonna time what? by doing this. This is gonna be the total of 12 meter. So you times this one by the 12. Okay, and then over here is what? Is have the 60 kilonewton meter, and 60 kilonewton meter gonna rotate what? Gonna rotate like this in the opposite direction. So this is going to be equal to 60. And then you got the c sub x of 60 divided by 12, and your c sub x gonna be 5 kilonewton. Okay, when you get c sub x of 5 kilonewton, you put it here, and then we can calculation for c sub y. Okay, by doing this, you may get c sub x of 5, and then you get the c sub x of 5 here is just in opposite direction, and then you have the what? The c sub y. This is 60 times plus this divided by 8. That is 42. When this one is 42, this one gonna be 42. Okay, and then things gonna be easier if you take a look at this, because for the column, if you have the c sub x of 5, so d sub x is gonna be 5 kilonewton. Summation of f sub x equal to 0. And then you may have the summation of f sub y equal to 0. And then you have the d sub y equal to 42 kilonewton. Like this. Okay. You have this 5 and you have this 42. And then you come to the frame A, B, C. Okay, the frame A, B, C, you may see in the x direction, you may sum of f sub x, okay, equal to 0. Okay, equal to 0. The mousepad is bad. Equal to 0. And then you have the c sub x here. You're gonna find what? A sub x. When you're gonna find a sub x, put this direction of a sub x as positive. So you will get for your a sub x. So you get this one for a sub x, and the c sub x is in opposite direction, minus 5. Okay, and you also 36 in opposite direction, that is minus 36, and then that's all equal to 0. So a sub x going to be minus 41. Okay, and the last one, you have the summation of what? Of f sub y equal to 0, and then you get the a sub y upward. You put the upward as the plus, and then your a sub y up. Okay, up. And then what you have is 42 also up. Okay, 42 also up, plus 42. And then the 15 is down, so you got to minus 15. So by this way, it's going to be equal to 0, and you will get a sub y equal to what? Equal to minus 42, and then plus 15. So that means you're going to get, it's going to be minus what? Minus 27, right? 27 kilonewton and meter. And you get this one for minus 27. What it means is a sub y is going to be downward. Okay, now we need to divide the frame into 3 pieces. However, the column on the right already divided, so we only have the column AB and the beam BC. Okay, let's start by doing this. We need to summation of f sub y equal to 0. Okay, we have to find b sub x, summation of x sub x equal to 0, and then the b sub x have this direction. You have this is positive, so the b sub x is going to be what? B sub x is here. This is going to be what? If you know, remember it. This is 12.3. That is 36 kilo Newton. This is 36 kilonewton. So the b sub x gonna plus what? Plus the 36. Plus the 36. Plus the 36. I don't know how come the ball pass still move up and move up. So this one is 36, and then we have this a sub x of 41 in the opposite direction. This one, this is the opposite direction, so minus 41, and then equal to 0. So we get the b sub x of 5 kilonewton. And then you do the summation of f sub y. You do the summation of f sub y equal to 0. And then you have this one for the b sub y is up. Okay, and the b sub y is easily to find. B sub y is up 27. We get is downward because it's minus, right? So d sub y is going to be equal to 27. Okay, 27 kilo Newton. This is going to be 27 kilonewton. And then m sub b, you better to take the moment here. So I'm sorry, the mouse just moving. It's pretty hard to control it. I will buy the pen later. Okay, m sub b equal to 0. And then what we have is what? The direction of m sub b to be counterclockwise. So taking counterclockwise as the positive. So the m sub b here. M sub b here gonna be what? Gonna be plus this one. Okay, that should be plus 36. And 36 gonna have what? 36 gonna have what? 36 gonna have this length. And this length is half of 12. This is gonna be times 6. And then we have the 41 in the opposite direction, minus 41. And 41 gonna times 12. And then it's gonna be, okay, equal to 0. So what you get is what? Is gonna be 246 kilonewton meter. Okay, let's check is correct or not. You just stop the clip and put it into your calculator. So what is going to be the shear diagram? Shear diagram start from here, 0, and end up here for 12 meter. Okay, and it's going to start by a sub x that's moved to the left, and then after that you get this is 3. So all of this, the s, the slope, dv by dx gonna be equal to minus 3, and that's why the graph going to get downward here. And over here, if you don't know it's going to be 5, you consider this. This is going to be the force that's going to move from the left to the right, and to be 0 here. That means this is V5 and move here. And if you don't believe it, you may put V over here, sub B, and then you minus 41, and then it's going to be equal to minus of the area here. The area here is 3 times 12. It's going to be 36. Okay, if you do this, see, it's going to be minus 36 plus 41 is going to be 5. Okay, that is right? And then for the shear diagram, you start at the A. The A has the moment of 0. Okay, and then anyway, when we have the shear force of 41, so put some highlights here. You hear force of 41 here. So the slope here, the slope here is going to be plus 41. The S here, S here is going to be 41. And then the slope just gets smaller and smaller until it reaches at this point. Okay, at this point. And at this point, the slope is what? Okay, the slope here is what? What the slope here is? Sure, the slope here is supposed to be 5. So we put the slope here of 5. But we still don't know the value of this yet. We know this is going to be S equal to S. You're supposed to write it beautifully. This one is very hard to control the mouse to draw it. Okay, and what we have is going to be, what is going to be the value of here is going to be the m sub b, and then it's minus 0, m sub b minus 0, and is equal to what? It's going to equal to the area or the area here, or here is going to be 1/2 of what? Of 41 and plus 5, that is going to be 46 divided by 2 is 23 times 12. Okay, you will get 276 if you tie 23 times 12. So, and then finally you got what? You got the m. This m is what? Counterclockwise, so it's negative. So it's take from positive here and goes down to here. Okay, next we have the what? We have the member here. Okay, from the what we have here, by the third law of Newton, we get this 5 kilonewton from the shear to the axial force of the beam. The axial force of 27 change to the shear force of 27, and the moment is here. And then we draw the shear diagram. Okay, for shear diagram, and we start from the B to the C. When we start from the B to the C, the 27 gonna be downward, so it's going to take this downward. Okay, and since there is no distributed force, this is 0, so this is still minus 27, and then it has this 15 kilonewton downward, so this downwards for another 15, so this one is 42, and then over here S equal to 0 until it's reached here, and then we have 42 kilonewton here, and then it closes the shear diagram. Next, the moment diagram. This is what? This is the clockwise moment, so it's going to produce the positive moment here, and then we have this one for 27, so the slope here is going to be minus 27 until it reaches here. What the value moment here? M here, minus 276, and it's going to be equal to what? It's going to be equal to the area here, that is going to be minus 27 and then times 4. Okay, and then you get the moment of plus 168. Okay, just move this one, and then the shear is minus 42 now, so the S here is going to be minus 42, but the point C is the what? The point C is the pin. The moment here is 0, so no need to compute, just drag the line here, you get the moment diagram from the beam BC. That's not hard, right? It's pretty easy. And the last one. And then we draw from the left to the right. This one, sorry, was from the bottom to the up to the top, sorry, from the D to the C. And then when we see this, we have this one is to the what? Right. So this one is pointing to the right. When pointing to the right, this is going to be -5. And then since there is no distributed force, slope is 0. So it hits this with -5. And then we have this force to close the shear diagram. Okay. And for the moment diagram, this is what? This is 60 kilonewton meter. Is what? Is clockwise. With clockwise what? Is positive. Okay. It's going to be positive 60. Okay. And then the shear is minus, so all the slope here is going to be -5. And then you see there is no moment, so the moment here is 0. So this one just move with the slope of -5 to be 0 here. So that is the whole moment diagram that we have. And again, don't forget to put the value of the moment or shear in is important point, and I also like you guys to put some point. This is not that good. Let me put. What happened this one? Put this one in blue. Okay, this is going to be the slope. Okay, and this is going to be the slope. You got to put this one, put this one, and put this one. Also indicate the slope. Put this one. What is the slope of this point? What we have, just put the value of the slope into it. This is what this would be, is S equal to, this one is S equal to, this one is S equal to, this one is S equal to. You got to put the magnitude and the slope of each important point, because the slope will tell you the shape of the graph. Okay, and the magnitude will be also corresponding to the slope. Okay, and then we have the end of chapter 4, and I will show or demonstrate you how to solve the problem by handwriting later.
This script is another script that going to talk about the shear diagram and bending moment diagram of the rigid frame for the study of chapter 4, the analysis of statically determinate beam and frame. And the final product of this analysis used to be the maximum shear and the maximum moment. And the maximum shear and the maximum moment can only determine by drawing the shear diagram and bending moment diagram. And if you may recall the analysis of the beam and the frame, we will start by draw the shear diagram of the structure, and then we use the equation of equilibrium to determine the reactions and the support of the beam or the frame. And then we use the graphical method, or we may use the equations of the shear force and the equations of the bending moment to draw the diagram. And if you recall, the method of writing the equation is kind of tedious and cumbersome, especially when the structure must be considered too many sections. For example, like this one, you need to consider this 1, 2, 3, and 4 segments. So you need to cut this structure for 4 times and determine the 4 equations of shear force and the 4 equations of bending moment. And then you put all the value from the equation into the graph, and finally you put the diagram. That's kind of tedious. The graphical method is kind of easier. You're going to use the distributed force, shear force, and the bending moment in writing it. So this example will use the graphical method to determine the shear diagram and moment diagram. Okay, the frame is look like this. It has the A as the roller, and the B as the pin. It's supposed to be the pin. That's not correct. The pin support. And then when it has the roller here and it has the pin here, we're going to have only T and no force. So this rigid frame is a kind of statically determinate frame. It can analyze by only the equation of equilibrium after we draw the free body diagram of this structure. Okay, let me start. We have the frame here. So the first thing, we're going to draw the free body diagram of the frame, and then we use the equation of equilibrium to what? To find what? To find reaction. Okay, we have three equation, we have three unknowns, so we can do that. Okay, let's make a copy of this. This is going to be 1.5 meter. This is going to be 2.5 meters. So we have the frame. This is the AC column, and this is going to be about 3 centimeter. Put this is 3 centimeter, and this is going to be the E, and half of this is this point. Is the point D, and we have this for another 2.5 centimeter. Okay, when you draw the free body diagram, it's better trying to just make a copy of the figure, and don't forget to put the reference X and Y axis. And you have this is point B, and we have what? We have the force acting content, and the first one is uniformly distributed force taking from the left to the right. So this is the uniformly distributed force. This may be the wind load. Okay, just apply to the size of the frame. The value of this is 0.4 kilonewton per meter, and we have 6 kilonewton here. That is going to be 6 kilonewton, and 15 kilonewton here. That is going to be 15 kilonewton, and then another one that is going to be 10 kilonewton. So we have the reference axis. We separate the frame out of the support. We put the no forces into the frame, and then we have unknown at A. That's it going to be A sub Y, because most of the force downward. We also going to have this one for the B sub Y, and since the distributed force put from the right to the left, and then we have this as the B sub X. Finally, don't forget to put the length. This is 4 meter. This is 4 meter. And since this one is 8 and this one is 4, so the rest of this also 4 meter. And this is going to be 7 meter. Okay, that is our free body diagram of the frame. And then we use the equation of equilibrium. Let me say, it start by summation of the moment about B equal to 0 to eliminate the B sub X and B sub Y, and to determine the A sub Y is going to be rotate clockwise about point B, and the A sub Y, if you take this, the A sub Y gonna time what? The A sub Y gonna have the moment arm about this. That is going to be 8 meters, so it's going to be 8 A sub Y is counterclockwise. And then we have this resultant of the uniformly distributed load of 0.4 kilonewton per meter times the length of 7 meter, and we have this for what? 2.8, right? This is supposed to be 2.8, kilonewton. And this is going to rotate in the opposite direction with the a sub y, so it's minus 2.8. And what is going to be this? This is half of the 7 meter, so it's going to time the 7 divided by 2, that's going to be 3.5 meter. And the 6 kilonewton have produced no moment here. Okay. And what else? We have the 15 kilonewton. That's 15 kilonewton gonna rotate like this, the same as this one. So it's going to be minus 15. And the line of action is here. And we see this is going to time what? 4 meter. And then we have the last one, that is what? 10 kilonewton. So the 10 also in the opposite of a sub y, so it's going to be minus of what? Minus of 10. And then the moment arm here is 8, so it's going to have 8, and all are 0. So you may put this into your calculator. Please stop the clips if possible. You may put them into your calculator and check if you get the same as me. I got this one of 18.725 kilonewton. That's for the a sub y. And then we go further. We have the a sub y already. Okay, just summation of f sub y equal to 0. What we have is the vertical direction is going to be positive. Okay, and then we have the b sub y, plus, now we got this already, the a sub y is 18.725 kilonewton, so it's plus 18.725. And then we have 6, 15, and 10 downward. If you like, we may put this equal to 10 plus 15 and plus 6. That is going to be 31. And then the 31 minus this, you're going to get the b sub y of 12.275 kilonewton. It's 31 minus 18.75. Okay, so you got this for 12.275 kilonewton. And the last one we have is the b sub x. So summation of x sub x equal to 0. The b sub x put to the right, so just put this one to the right is positive. So we have our b sub x. And then the b sub x will resist what? The horizontal force, maybe from the wind load that I said, is going to be equal to what? Equal to 2.8 kilonewton. And then we have this, so this b sub x is going to be equal to 2.8 kilonewton. So now we have the reaction of the frame, and then we're gonna separate. Okay, the second, we're gonna separate the frame into 3 pieces. Separate the frame into 3 segments. Let's call them segment and draw the free body diagram of the segment, 3 of them. After you finish drawing the free body diagram, you use the equation of equilibrium to find. Actually, we find the end moment and end shear force. That is gonna be the V, and end moment. Okay, that is gonna be the M, and also and end normal force. Normal force, that is gonna be N. That is gonna be N. Okay, that's all we are going to do. And by doing that, we got to clear up our area. Okay, we have the beam, we have the column. So I think it's better to try to make this beam is 8 meter. Just put them in the 4 centimeter, and then this is going to be half of it, and this is point D going to have this, and this one also have the column. Let's put the column a little bit far away here. The column is going to be 2 centimeter. Let's see, let's put the column into this. Okay, and let me move this one a little bit more, and this one is going to be 2 centimeter. Why I draw is here like this? Because I like to have some area here to draw the shear diagram and moment diagram. That's why I put it there. So this one I'm going to put in this direction. So I may put this one here. Okay, we have the whole column. This is going to be CDE, and this one going to be EB, and this one going to be AC. And what we have is the obtained reaction that we have. This one is going to be 12.2. So move a little bit more. Okay, 12.275 kilonewton, and it has to be sub x in this direction of 2.8. Let's see, there's 2.8 kilonewton, and here is 18.725 kilonewton. Okay, and now we will apply the known force, and this problem we need to consider the joints, because the joints also subjected to the force. This is 10 kilonewton. This is going to be 15 kilonewton, and we also have the joint E here. The joint E subjected to this one of 6 kilonewton. And then let us consider from this. When we consider this frame, we may see this 18.71 summation of f sub y equal to 0. This one gonna have 18.725 kilonewton. Is there going to have shear? No shear, and also no moment, because the force is axial in the axial direction of the column. So just put summation of f sub y equal to 0. We obtain this. Okay, and then the 18.725 gonna act upward over here. And then if you do the summation of f sub y equal to 0, you will get what? This is going to be up for 18.725. So we're going to have the shear here. Okay, let's have this one, V sub C. The V sub C. We see that one. V sub C plus 10. Plus 10 is going to be positive when downward. And this one going to be in the opposite direction, equal to 18.725. So you will get the V sub C equal to what? 8.725 kilonewton. And there is no axial force and no moment. And this V sub C is going to be act at C here, but the direction by the third law of Newton, this is going to be 8.725 kilonewton upward. Okay, if you move again, you will see that we will have the V over here. This is going to be what? This is going to be, let's say, V sub E. So you do the summation of f sub y equal to 0, and then you are upward positive. So the V sub E is up plus 8.725. This is up, and then it's going to equal to 15. Okay, and then you may have your V sub E equal to 15 minus 8.725. Okay, and then you will get V sub E equal to 6.275 kilonewton. Just put this one equal to 6.275 kilonewton. And this one going to be by the third law of Newton going to be down. Okay, and also this is the rigid joint, and since this is the rigid joint, this is going to take the moment due to the forces about this and about this. Okay, is is going to have some moment due to these two force. So this is going to be m sub e. And you can determine that m sub e summation of moment that take moment about this. Okay, m sub e equal to 0. And your m sub e going to rotate, let's say, this way. And what's going to be what? The m sub e. M sub e what? M sub e going to rotate like this. And this guy going to rotate in the way of m sub e. So plus 15. And don't forget, this is 4 meter. This is 4 meter. 15 times 4. That is 60. And this moment have the opposite direction. So it's going to equal to 8.725. And this 8.725 going to time what? Going to time 8. Okay. If you put everything there, you will get the m sub e, okay, equal to 9.80 kilonewton meter. So this is equal to 9.8 kilonewton meter. And then this is going to apply here. Okay. By doing that, this force is downward, apply here. And this force is 6.275. And we also has, this is 6 kilonewton. So the force here, the force here, the summation, if you summation of f sub y equal to 0, this may be n sub e. You may get n sub e equal to 6 plus 6.275, 6 plus 6.275. So you get it for 12.275 kilonewton. So you got this. And since this one is 12.275, so this one also apply here to be in equilibrium. And then this moment, okay, when you sum the moment about E, you're going to have this moment also, and there where you're going to be equal to here. And finally, if you put it with the third law of Newton, and you will get this one of 9.8 kilonewton meter. That is going to be m sub e also, right? And what? And do you have the force applied to here? Yes, we have the uniformly distributed load here, and you guys need to check the result, such as summation of the vertical force is 0. Yes, it's 0, is equal. And then this, from the previous calculation, we have this for 2.8. So this is going to be 2.8 kilonewton. And then the summation of f sub y equal to 0. Okay. And finally, you can check the moment here, 9.8, also in equilibrium. So that is the second step. And the last one, we will draw the shear diagram and moment diagram of the frame. Okay. By doing that, we're going to draw the diagram by the column. We will draw from the AC to CE and then to the EB. Okay. And when you draw the when you draw the shear diagram and moment diagram of the column, it's better, a good idea to rotate it to be like this. Okay. If it rotates like this, it's going to be more convenient for you to draw the diagram of the column. And then this is going to be what? This is going to be the x meter, and you may put this as the V kilonewton. And what we have is there is no shear here, so shear here is 0, and shear here going to be 0. This is 0 meter, and this is the length of the column is 4, because this is 4 meter column. And also, if you draw the moment diagram, this is going to be x meter, and this is going to be the m kilonewton meter, and this is 0 meter, and this is 4. What you get is the moment here also 0 kilonewton, and this is also 0 kilonewton. This column only has the normal force, okay, and the normal force is in what? Is in compression. This is going to be in compression, and if you put this is the positive normal force kilonewton, So you get the negative, okay, of what? Of 18 minus 18.725 kilonewton. And it is constant along its length, okay, until it's here. It's going to close like this. And if you put the slope here, also be 0. Okay, that is the first one. And then you may rotate to the shear diagram and moment diagram of the beam. So let's project this E, C, and D. Okay, and we have the shear diagram here. So we start by putting this one. Let's say this one is the X meter, and you have this is shear kilonewton, and this is 0 meter, 4 meter, and 8 meter here. Then we start from the C. When we arrive at C, we got the shear force of 8.728. So this is scale of 1 millimeter for 1 kilonewton. So this is about this 9 millimeter, 8.725, okay, millimeter. So this is plus 8.725, and kilonewton is here, okay. And then you move to the segment CD, and there is no distributed force. So the dV by dx is 0. So this one is the constant, and S is 0. Then you have this one plus 8.725. And the 15 gonna take this point down for 15 millimeter. So it's gonna take this one for 15 millimeter because of our scale. See, if you scale it, it's gonna help you 1 millimeter for 1 kilonewton. So this one gonna be what? Plus 8.725, and then minus 15. You will get the shear force of minus 6.275 kilonewton. And then again, there is no W here. So the slope here gonna be 0. This value gonna be constant, or minus 6.275. And then when you arrive here, you have what? You have the V sub E of 6.275. If that's the case, what we have is this one is close. Okay, that's very clear pictures. And next, we may draw the moment diagram. Okay, we draw the moment diagram here. This is going to be again the X. The X is 0, 4, and 8. And up here is the moment. This is going to be M kilonewton meter. And what we have here, at this point, there is no moment. So we start with 0 kilonewton meter at 0. And then what we have is what? The shear of 8.725, and it is positive. So when it's positive, the graph supposed to be up like this. This is positive shear, or also positive slope, and this is going to be negative slope. This is minus S. This is plus S, and 0 is in horizontal. What we have is it's going to be plus, but we don't know the magnitude of the moment here. We can find by what? By the moment here, minus the moment of here, moment after minus moment before. Okay, it's going to be equal to the area, of the shear diagram. So that means it's going to equal to this one. Okay, and then you can just put the what? 8.725 times what? Times this one, that is going to be 4 meter. So times 4. Okay, and you may stop, put it into your calculator. You may get the M here equal to 34.90 kilonewton meter. So let's see. Let me set this one is going to be 34. So this is 30. Okay, this is 10 for 5, 10, 20, 30, and this one is about 34. Okay, this is going to be 34.9 if you like, kilonewton meter. If you like, just put it kilonewton meter. And then the scaling gonna tell you this is going to be the line of moment diagram, and with the slope of what? Of plus 8.725. Okay, then the slope that change, this one slope change to minus value, okay, minus 6.275. That's going to be the new slope. And what is going to be the moment here? Okay, and see, you know it already. Actually, the slope, sorry, the moment that's x there is what? The moment x here is 9.8. Actually, you know this one is 9.8 already. But if you like to check which is going to be the slope here, that is going to be m. Okay, m is here, minus 34.9. M after minus m before. And then that's going to be equal to the area here. Okay, it's going to be equal to area, and the area here is negative. It's going to be minus 6.275, and time what? And it's gonna time 4. So this side is negative, and when you move this, it's going to be plus, and the value gonna reduce. Okay, that's your guy. Put it into your calculator. Stop the clip. You will get the moment here of, for sure, 9.80 kilonewton meter. So this is going to be 9.84, and then you scale it with what? With this 1, 5, 4, 10. So it's going to be about this, and then your graph in this section going to be here with the slope of minus 6.275, and you get what? You get this m sub e. Okay, this m sub e is going to be counterclockwise, so it's negative. So it's going to take this one down to close to this. Okay, and also, do you have any axial force here? There is no axial force here. Since there is no axial force here, so we have no n diagram. So if you like to put the n diagram is just simple as n kilonewton, and it's 0 kilonewton here and 0 kilonewton here with 4, 0, 4, and 8 for x here meter. Okay, now the final one. The final one, we have the column again, and it's better to rotate this in this direction. Okay, and then we draw the line for it. Okay, and what we have here is again the shear diagram, and we just put the shear diagram in this. Oops, sorry, in this horizontal direction. Okay, and this is going to be x meter, and this is going to be 3 kilonewton. And from this, what we have is the force here. The force here is 2.8 kilonewton. So this is going to be 2.8 kilonewton. Let's put this one. That's 5.6 millimeter. Okay, and time this for 2 times. We have 2.8 to 2 is 5.6 millimeter. Okay, we have the scale. So it's going to be downward. When it's downward, this is going to be minus 2.8 kilonewton. And then what? And the W here is in the upward direction. We have the dv by dx equal to minus W when W is put downward. So this W is in opposite direction. So it's gonna be plus, since this one is opposite direction. So the S here is gonna be plus of what? Plus of 0.4. And then here there is no shear force, so this is 0 kilonewton. And then we'll just draw this shear diagram. Really beautiful one. Okay, right? And next. Next, we draw the moment diagram. Again, this is x meter, and the moment is going to be here, the moment kilonewton meter. We start again with the point B. There is no moment, that's why I put it here. That is 0, and the length is going to be what? 0 meter here, and going to be 7 meter here. What we have is there is no moment, and moment here. And what we have, this one is going to be what? This one is going to be 2.8 and negative. So the slope, the dm by dx, is going to be negative. That means we're going to have negative like this, because if this put to this one, the slope here is plus, slope here is 0, so slope here is negative. And then we have this of s equal to minus 2.8, and then it's going to be here. And then the value of this reduce until up here. I don't know how much it is, but the slope here going to be 0. So over here we will have s equal to 0. And what is the value of moment at this point? Actually, we already know that the value of moment here is going to be 9.8. Okay, this is 9.8. So when it's going to be here, and since it's downward, it's going to be minus 9.8, if you like. And if you don't believe, this is going to be point E, so we may have the m sub E. Yeah, the m sub E here minus m sub E. Let me put this in pink. Minus the origin of this, minus 0, and then it's going to be equal to what? It's going to be equal to the area here. That is going to be 1/2 of 7 meter, and then time minus 2.8, and your m sub E is going to be minus, this is 1.4 times 7. 1.4 times 7 is going to be minus 9.8 or kilonewton meter. So going to be value of this. So that means it's about 1 centimeter. Goes to here, and the slope here is 0. So if you draw the graph going to be in the curve, okay, from here and then to here, with the slope here going to be this, and slope here going to be this. And the last one, we have what? We have the axial force diagram, and the axial force here is 12.278. It's going to be negative. So if we put this one as x meter, and we put this one as the n kilonewton, the axial force here is negative. So just put it one negative. Negative of what? Negative of minus 12.275 kilonewton. And it's always constant. So it's always constant. Going to be like this, and it's goes like this. S here equal to 0. Okay, that's the way we draw the shear diagram, moment diagram, and the normal force. And if you do next, what is you should do next? The next thing is trying to combine what we have all here to the proper graph. Okay, usually we should draw it with a bigger scale to make it more understandable. Okay, by doing this, let me put this one into the same figure. Let's zoom it a little bit. Let's see, this is going to be 8, so it's going to be and this is going to be 2 centimeter, and it's going to be 7, that is 3.5. Okay, and for the moment we do the same. We just put it a little bit down here because we like to have some space for that. Okay, this is over here, and this is 4, that is going to be 7. And if you lift it up a little bit, you will have a clear picture of this. And what we have is, we start from the shear. This is going to be the shear diagram of the frame. This is shear diagram of the frame. And if you put this one, you start by the shear diagram of this. The column AB has no shear force, so it is 0. And then we have this for 8.725. So let's put this one with the scale of 1 kilonewton per millimeter. So it's going to be 8.7 to up like this, and plus 8.725 kilonewton, and it's constant up until here, okay, with the slope of 0, and this is still plus 8.725 kilonewton. And then what? And then this downward to minus 6.275, so that's it's going to be 6 millimeter. Okay, this is minus 6.275, and the slope is 0 again. Yes, equal to 0. So when you draw this, you're supposed to draw it clearly, okay, to make everything on scale. When it's on scale, the size of the picture will help you a lot to understand what's going to be. And next, this is minus 2.8, so that is going to be 2.8 millimeter. Okay, and then it's going to be the shape like triangle here. And then you have the S here of what? Of 0.5. So S here equal to plus 0.4, and the value here is gonna be minus 2.8 kilonewton. Okay, you put what? You put the slope clearly. Okay, clearly. You also put the value and also the unit, okay, of this clearly. But this one is going to be kilonewton also. That is a beautiful shear diagram. Next, for the moment diagram, we have the M diagram here. Okay, for the M diagram, we come to this. The column AC also has no moment, so there is nothing there. And then you just copy this one and you see the scale, same scale. And before that, you have this for what? For 4 meter. Okay, this is going to be half 4 meter here, and it's going to be 34.5. So if you have, this is 10, 20, 30, that is about 34.5. So this is going to be, sorry, 34.9 kilonewton meter. And then you got to put this line over here. Okay, it's up a little bit, it's okay. And then we have the S here of plus 8.725. Okay, and this is gonna be what? 9.8. So it's about 10. So it's about this. This is going to be 9.80 kilonewton meter. And you got to draw this line also. And the S here is what? The S here is equal to minus 6.275. And the last one over here, the moment here is 0 kilonewton meter. And then it's up with the S of minus 2.8. The slope is minus. So just put this one here. And you may set this is S equal to minus 2.8. And then it has the value of moment here of 9.8. You put this one is 9.8. The same as this 9.8. And the slope here is 0. So you put the slope here, and here is 0. I put the same red letters for the slope, and then you just draw this. You have to be very, very careful to draw this. Okay, just do a little practice. So your graph is going to be very beautiful, and you may highlight the value of the moment. That's important. It's going to be 0 here and 34.9 here, and this is going to be equal to 9.8. Even though it is kind of a negative here, but actually it's due to the sign convention. This is going to be 9.80 kilonewton meter, and then you put 0 here. And the last one, you got to highlight the slope. That's going to be the slope of S, slope of S, and this is minus 2.8. This is 0. So what we have for the Vmax? Okay, for the Vmax we have Vmax for the beam and for the column. Let's conclude this must be 8.725 kilonewton. That is our Vmax. For the Mmax is here. What? 34.9. That is going to be equal to 34.9 kilonewton meter. You got this. Okay, that is the shear diagram and the moment diagram. If you like further to draw the axial force diagram, it's not that hard. If you like, just do it. Okay, this is going to be 2, this is going to be 4, and this is going to be 1, 2, 3, 3.5. And this one to be the normal force diagram, the N diagram. What we have here is, going back, the normal force here is minus what? Minus 18.725. So that is going to be kind of a large one. That's going to maximum. Let's put this is 10, and the 18 minus 18 supposed to be about this. Okay, and it's going to be a constant of minus 18.725, and then it's constant here, and close here. Okay, and the shear has no axial force, and we also has minus 12.275 kilonewton. Okay, that is about this, minus 12.2. Okay, this is about this. Okay, 6 millimeter, and let me put this one for minus 12.725 kilonewton. Let's put the kilonewton here, and the line gonna be like this. Okay, and then it's going to close here, and then we may conclude the Nmax equal to minus 18.725 kilonewton. That's going to be the compressive force. Okay, so that is the result that we obtain by the analysis of the statically determinate frame, and you may see clearly if you put effort onto it, you may get all the magnitude of what you like to determine very clear, and if you carefully dot it, you will get very beautiful graph. Okay, that's going to be the whole detail that we have. And don't forget, after you finish this, what you have for the Mmax, if you remember, the Mmax going to be 34.9 kilonewton meter. Your Vmax is going to be 8.725 kilonewton. You are sorry, this is going to be only A sub y. This is going to be A sub y, and this is going to be B sub x, and this is going to be B sub y. And then what we have, the B sub y is 12.275 kilonewton, and it's upward. The B sub x is going to be 2.8 kilonewton in this direction, and A sub y is 18.725 is upward. Okay, that is the final product of what we do for this example. I think it's worthwhile to watch the video, and you can stop the clips when you need to do the calculation to see you can put the number into the calculator and get the same result or not. And you should watch it and do it by yourself, not just watch it and then finish. This is not a movie. This is the demonstration how you guys to solve the problem step by step. Okay, let's finish of this script. Hello, this script is a clip that I'm going to show you how to draw the shear diagram and the moment diagram for the rigid frame. The rigid frame in this problem has the support, and A is the fix, okay, and the P and the C is the pin, and it has the rigid joint at B. This frame is going to have the reaction at A, that's going to be 3 of them, the A sub x, A sub y, and also the moment M sub A is a fixed support. And then it's going to have the reaction, what, C sub x and C sub y here. The frame gonna have 5 reaction, and we have only 3 equations of equilibrium for this frame. So this frame is going to be statically indeterminate frame with 2 degrees of indeterminacy. However, the problem gives you that's 2 unknown degree of indeterminacy. They provide you with the A sub x of 10.23, and it's going to put to the right. That means this one is going to be 10.23 kilonewton. And it's also provided with the A sub y upward of 27.42. So by doing this, you will have only 3 unknown left to determine the reaction. So let us start by draw the free body diagram of the frame, and then we will use use the equation 3 equation of equilibrium to find the reactions. Okay, then we're going to have this, our frame going to be 4 meter here and 8 meter here. So this is going to be 2 centimeter for 4 meter. This is 4 meter. I put it for 2 centimeter, and then we have here, and this is going to be 4 centimeter for 8 meter of the frame. And following that, we will have the applied uniformly distributed load here of 6 kilonewton per meter. So this is going to be 6 kilonewton per meter. And for the given information, so we have this one of 10.23 kilonewton, and this one of 27.42 kilonewton. And then we have the unknown M sub A here that is rotated clockwise. And in this support, we have the C sub Y and we have the C sub X. Okay, we have the reference axis, we have the free frame, we have the applied force, we have the unknown forces, and this is 4 meter and this is gonna be 8 meter. So what next you can do on this? Okay, let's just use the equation of equilibrium. By using the equation of equilibrium, let me take the moment at A first. Summation of the moment at A is here. Okay, this is the A, B, and C. Take the moment at A. When you take the moment at A, this is gonna be what? Clockwise direction. So we will have this one for the M sub A. M sub A. When we take moment at A, the problem occur. The C sub X and C sub Y is an unknown. So we cannot take this equation yet. So we're going to left it. So sometimes we used to know that the moment is supposed to take first, but some problem it won't be like that. Okay, so we're going to take the summation of x sub x equal to 0. if we take that, we going to find c sub x. So we put this as the positive, and then our c sub x is going to in this direction. And then what we have is 10.23 is in the opposite direction. So the cx is going to be easily to find 10.23 kilonewton. Okay, and you put this one, the cx is going to be what, 10.23, the cx kilonewton, and the direction is like this. And next, if you know this is only 10.23 kilonewton, and next you do the summation of what? Summation of f sub y equal to 0. By doing this, our x sub y is upward, so we put the upward is positive. This is c sub y, and c sub y has this 27.42 in the same direction. Okay, and this uniformly distributed load gonna have the resultant here, and the resultant gonna be 6 kilonewton per meter times 8 meter. Okay, and then what we have is just meter cut meter. That's going to be 8 times 6. That is going to be 48 kilonewton, and it's going to be in half of the 8 meter. So it's going to take 4 meter here and 4 meter here. And then this one is downward, so it's going to be minus 48. Okay, and then it's equal to 0. And then our c sub y going to be what? Going to equal to 48. And then minus what? Minus 27.42. And you will get c sub y what? You may stop the video clips and put the number into your calculator. You're going to get this for 20.58 kilonewton. Okay, if you type it. Now, you have this one of 20.58 kilonewton, and you also have this one already. So now the equation of m sub a equal to 0 is applicable. We have the clockwise is the positive. So you may see this force is going to rotate clockwise, so it's going to plus 48, and this 48 going to times this moment arm. What is this? This is 4 meter. So this is m sub a plus 48 times 4. And then what? And then you get this c sub y gonna rotate in the opposite direction, counterclockwise. So you got to minus, this is 20.58. And then the distance here is going to be the total of 8 meter. So it's going to times 8. And you also have the c sub x in this direction, and it's going to rotate counterclockwise. Sorry, counter with the m sub a. So it's the opposite direction. So it's going to minus what? 10.23, and 10.23 gonna times 4, and then this is gonna equal to 0. So by putting this into the calculator again, you may stop your clips and trying to put the whole number into your calculator and see what you get. Okay, and if you stop and you try to put this is going to be 13.56 kilonewton. So this is going to be 13.56 kilonewton meter, and it's going to rotate clockwise. So it's going to rotate clockwise like this. This is counterclockwise. This is clockwise. Okay, and also c sub y. You got c sub y of 20.58 and kilonewton, and put it upward. Okay, now you have your reactions. When you have your reaction, now you can use the free body diagram of each part, and then you can find the end moment, end shear, and then the next step after you find the end moment and end shears, also the end axial load, you will have a chance to use the graphical method to draw the shear diagram and moment diagram. So Next, we are going to separate the frame into two pieces. This is going to be the beam, and this is going to be the column. Okay, and also you have the joists. Okay, this joint going to be the joint B, and this is going to be A, B, and B, C. So next step, you will draw the free body diagram of the frame segment. So you have two segments, A, B, and B, C, and use the equation of equilibrium to find n, v, and m. That is going to be n of the member, normal force, shear, and moment. And again, you have the distributed force for the beam BC. Okay, of what? Of 6 kilonewton per meter. And what you get from the calculation of deflection, this is again gonna be 20. Oh, sorry. Next one. That is going to move a little bit. Okay, that is going to be 27.42, and this is going to be horizontal force of what? Of 10.23 kilonewton. And you have the moment m sub a. Okay, in this one going to be m sub a going to be 13. This is kilonewton, 0.56 kilonewton meter. And you also have this at the c sub y, and then you have it for 20.58 kilonewton. And the c sub x, you have this for 10.23 kilonewton. Okay, so now it's up to you when you like to determine the end forces and moment at the end of the beam and end of the column. And let me try to determine first by this piece BC, and let me have set this force as the V. Actually, it's supposed to be V sub B if you like, and also the force here is going to be N sub B. Is a normal force, right? And also the moment that acts here is M sub B. Actually, I got the direction of this V sub B because this force is going to be 20.58, and you know from the previous calculation that's the resultant force here going to be 48 kilonewton. So the V sub B for sure is going to be upward. And also the normal force at B, since 10.23 move to the left, so this one going to move to the right. However, for M sub B, you got to give whatever you like. Okay, and if it's negative, the SI direction going to be wrong. Okay. And then from this, we may go a little bit further to determine the internal forces and moment at NB of the beam BC. Which one you like to use first is up to you. You may use the summation of x sub x equal to 0. So you got the N sub B like this. So your N sub B gonna be what? Your N sub B gonna equal to 10.23 kilonewton. That's going to be the first one, 10.23, and you may put this one equal to 10.23 kilonewton. And next, you may have summation of f sub y equal to 0. By doing this, this is V sub B, so up is plus. So your V sub B is up, is going to plus 20.58. These two upward. And 48 is downward. If you like, you may just put it equal to 48. And then your V sub B gonna be 48 minus 20.58. And then if you stop the clips, you may have a chance to put them in your calculator, and you will get this for 27.42. This is 0.42. Okay, you get this V sub B of 27.42 kilonewton. And let me mark this one. This act at the centroid of the rectangular area. So this one going to be 8 meter and 8 meter. I got to put this because the next equation we're going to take the summation of moment. And let's take it about the B. The B equal to 0. And now this direction, let's set is positive. Okay. So what you get is the moment at B counterclockwise, and then you have this one. These two forces have 0 moment, okay, because it's at the point of B, no moment arm. This one gonna rotate the same direction, so plus what? Plus 20.58. And this 20.58 is oh sorry, it's wrong. It's going to be 8 meter apart. Okay, that's the main arm is going to be 8 meter between B and C. And then you have this as the opposite moment. So you may get this one equal to 48. And then it's gonna time the length of 4. Okay. If you do the calculation, you may stop now and put the number into your calculator, and you will get the M sub B of M sub E is the moment, kilonewton meter. That's M sub B gonna be what? This one gonna have the value of 164.64. Okay, and this is gonna value of 192. Okay, if you minus 192 with this, you're gonna get M sub B of 27.36. Okay, now you get this guy of 27.36 kilonewton meter. Now, and you may see the B has no force and moment. So actually you can transfer the normal force, the shear and the moment directly to the NB here due to that condition. And if you try to understand this, it will be show easily the N sub B. N sub B gonna be here. Okay, the V sub B by the third law of Newton, V sub B is downward. Okay, and then the moment when you transfer here, the moment gonna be this one. And then if you use this again, this one gonna be there. This one and this one gonna be equal. Okay, and this one is down, so this one gonna be up. Okay, gonna be up, and the moment here rotates like that, so the moment here gonna rotate like this. Okay, by doing that, if you do this again, you may see that the moment here is gonna be the moment here. Okay, that is gonna be 27.36 kilonewton meter, and the axial force here gonna be here. That is what? This one equal to this one equal to this one, 27.42. So this one gonna be 27.42 kilonewton, and the 10.23 velocity is this, and it's gonna be 10.23 kilonewton here. And now when you transfer to this, you may check the balance of the force and the moment. For this one, this is what? 27.40. This is going to be equal to this one, and also this 10.23, that is going to be equal to this one easily. And if you like to check for the moment, you may take the moment about A. Okay, let's check the moment about A. Summation moment about A equal to 0. and then these two forces produce no moment. You have only 13.56. So this one gonna rotate like this, and you have 13.56. And then what? The 13.56. You have this 10.23. This 10.23 also have this direction. Okay, so the 10.23 gonna minus 10.23, and this is gonna be 4 meter times 4. Okay, and by doing that, you may have what? This moment, the 27 plus 27.36, and you may see if you put all this number into the calculator, you will get the result of what? You will get the result of 0, and this is imbalance. So the moments you get are imbalance. Okay. Now you are ready for what? Ready to draw the shear diagram and moment diagram. And for this, you may extend, okay, the line like this. And then for this one, okay, you may make a copy of this one into here, and then you can draw it later here. Okay, let me just move this one here. Okay, and put the force clearly here. That is going to be 10.23 kilonewton, and this is going to be 27.42. This is 42 kilonewton, and the moment here is 13.56 kilonewton meter. And you have what? That is not correct. All right. This is the force of, oh sorry, this is going to be this force. Okay, sorry for this. It's going to be in this direction. So this one going to be in balance. If not, it's one. Okay, it's one. So this one has the wrong direction. It's going to be like this for the 10.23, the a sub x. And on the top, you get this one. Sorry on that. This one. This one is 10.23. This is 10.23 kilonewton. And you also have this one up, this one down, this one up, so this one down. This one also have this one for 27.42 kilonewton. And this one, you got this for 27.36 kilonewton meter. Okay, when you going to draw the diagram for this column, let me try to zoom it more like this. And you're going to start by what? Setting up this axis along the column AB, and this is going to be x meter. Okay, and what? And this is going to be the V kilonewton. And what we have is we are going to draw this from, this is 0 meter to this is going to be 4 meter, because this is 4 meter long column. And we will start by what? We will start by here. And what we have by the graphical method, that is the third step, is going to be what? We're going to have the 10.23. Okay, 10.23. If we set 10.23, that is going to be downward. Okay, this is going to be downward. We have this 10.23 from the graphical method. That is downward. And when it's downward, it's going to be minus 10.23 kilonewton. And then you move between A and B. There is no distributed force. So the slope here, dv by dx equal to 0. By that it means this one going to be constant. Okay, and then what? You arrive here. You have the upward upward for 10.23, and this one gonna close here, and your shear diagram for this member can be determined easily. Okay, and then next we come to this one, and what we have is this one going to be x meter, and the axis here going to be the moment in kilonewton meter. And what we have is we have this 27.42 rotate clockwise, and you guys know that if we have the clockwise moment, that means we going to have the oh sorry, we have this we have this not 27, we have this is going to clockwise moment, and 13.56, that 13.56 is going to be positive. So if you set 20 is like this, you may set this one is the 13. Okay, that is going to be plus 13.56. You don't need to put the unit because the unit is here already. And then what happened is you come over here, you draw the moment diagram, you take a look at shear diagram, the shear is minus. So that means this one gonna have the curve like this. This is for minus slope. If the slope is 0, is here. If the slope is positive, it's like this. This is minus. Okay. And you may wonder, this one going to be what? Actually, if you are really good on this, you can see there is the moment here for 27.36. Okay. If you don't care much, you may get directly into this. This is going to be 2 times of this, about that. Okay. This is going to be about a little bit larger than that. Yeah, okay, this is going to be like this, and this one going to be minus of 27.36. You don't need to put this, actually unit there because the unit is already here. And what you get is the S here is equal to what? Equal to minus what? 10.23. Okay. If you're not sure on this, you may prove the moment here is this value or not. Okay, let's check. We just the moment at what? At B. Moment B here. Let's see. We don't know about it. We have the moment at A here, so minus 13.56, and then it's gonna be equal what? It's gonna be equal to the area. Okay, under the shear diagram between that 2 points. So the area is going to be equal to minus 10.23, and then it's going to time 4. So your M sub B is going to be, let's say, plus 13.56, and then minus this number 10.23 times 4. And if you place this into your calculator, you will get N sub B equal to this number. Okay, that's going to be correct. And if you like, you may notice that we have the compression here. Okay, if you like to draw the axial force, you may set the N. Okay, you may set the N kilonewton here, and also you have the x-axis here, x in meter, and what you get, this compression is negative. Okay, 27.42. So this one going to be in minus of 27.42, and your axial load diagram gonna be like this. Okay, it's very similar to the shear diagram. Next we have the shear and moment diagram of the beam. Again, we set this one as the x meter, and you may see this is going to be what? This is going to be 0 meter, and this is going to be 8 meter, and the axis here of what is going to be V in kilonewton. Okay, we will start to draw from the B to the C, and if you may see what shear force do we have, and if you take this, you may see the shear force is going to be what? This is the normal force. The shear force is going to be this one, sorry, this one, right? 27.42. So this one gonna take up for 27.42. Let's say if this is 30, 27.42, maybe around here. Okay, this is 20.42 and it's up. Okay, that is, you use this number directly, and then you come over here, you got the 6 kilonewton per meter. That means your graph gonna be downwards like this, because the slope here, the dv by ds, is gonna be -6. Okay, if it's 0, it's gonna be horizontal. If it's positive, it's gonna be upward. Okay, so what the value this one supposed to be? If you guys are good and you are very detailed on this, you may notice this one gonna be 20.05, because the 20.05 gonna be the one that's close this. Okay, if this is 30, this is about close this. Okay, if you are not sure what is going to be here, you may say, okay, this is going to be V sub C. Let me put this in V sub C. V sub C here. V sub C here, minus what? Minus what? Minus 27.42. 27.42. And it's going to be the negative of the area of the distributed force. So this is the total area of it. The total area is what? Is 48. So it's going to be equal to minus 48. So we can compute the V sub C is equal to minus 48. And then you move this one plus 27.42. So you get your V sub C here of what? Of minus 28.58. And then kilonewton. If you like, you may put kilonewton. If not, it's okay. And what you have is the graph is gonna be twisted here, gonna be like this by proportion. You got to draw it proportionally. Okay, and the slope is there. And this point is the point of zero shear. The point of zero shear is important because most of the time the moment is maximum or minimum here. This is going to be what? You may compute this one again. This is 27.42. That's it. 27.42, and then divided by, this is the x, divided by the x, and then you have this of slope. This is going to be 6. So you can have x up and take the 6 down. So it's going to be 27.42 divided by 6. Okay, and you can find this x equal to 4.570 meter. Okay, that's for the shear diagram. And then for the moment diagram, we may put things into this, and we will again start from here to here. This is x meter, and the vertical axis is m in kilonewton meter. And now you move to point B. Okay, at point B you got what? You got m sub b of 27.36, and that m sub b is rotated counterclockwise. When it's rotated counterclockwise, this m sub b is negative. Okay, and this m sub b will have the value of minus 27.36. So this is minus 27.36 kilonewton meter. If you like, you can put. Okay. And what? Draw the moment diagram. You got to use the shear diagram. Draw the shear diagram. You use the segment of the structure. And since this one is negative 27.36, and then what we have is the shear here is what? 27.43. So you got the dm by dx equal to v. So you got this of the s equal to plus what? Plus 27.42. And then the value will, the slope will decrease up until here. The shear is 0. So the slope here gonna be 0. Slope here gonna be 0. And what's going to be the moment here? What should I do the calculation? Okay, I can do the calculation here. The moment here minus the moment here. The moment here is going to be m minus of here is minus of minus 27.36. Okay, and that is going to be what? That is going to be the area here. Okay, you're going to put this one equal to 1/2 of 4.57, and then it's going to time the shear here 27.42, and you put everything in your calculator. Your m can be like 35.3. Let's see, T4. Let's check kilonewton meter, and that is going to be the value of the moment here. Okay, if you put 1 centimeter at the 30, so this one gonna be kind of about this. This is gonna be the slope, and this is going to be the slope. So the curve is going to be upward like this. And finally, the C is the roller, so this is going to be 0 kilonewton meter. And then this is 0 slope. And over here, we're going to have dm by dx equal to v. And then, dm by dx equal to v. Okay, this is equal. V is what? V is 20.58 negative. So this is going to be the negative slope like this. And just put the S equal to minus 20.58 equal to this number. And then your graph is going to be downward like this. Okay, that is the way we draw the shear diagram and the moment diagram. Or if you like, you also draw the axial force diagram. You just extend this a little bit more. Okay, this is going to be shear diagram. You may say this is going to be V diagram. Okay, and this is going to be M diagram. Okay, and the last one, if you like to put over here, is going to call the N diagram. Okay, the N diagram. And you may see if this is X meter, the force acting in this member is again compression. So it's going to be downward. Compression of what? 10.23, the same as before. This is going to be in the compression. Unlike previously, the column is in compression of 27.2. This is going to be minus 10.23. And if you put this one as the N kilonewton, so this is going to be constant force, and this is minus 10.23 kilonewton, and they are all equal. And this is going to be the axial load diagram. Okay, and finally you got to find the maximum shear and the maximum moment. And you may see the maximum shear for the column is not equal to the maximum shear for the beam. So when we decide it, we supposed to separate the design of the beam and the column. Also, the maximum for the moment is here is 35.34, and the maximum for moment for the this one for the column going to be here, and maximum shear is here. For the maximum shear of this is like this. For the maximum axial force, they are different. This one is equal to minus 10.23, and this one is minus 27.42. Okay, and in many times Ajahn also asks you to combine the frame to obtain the final final shear force diagram and final moment diagram. Let me a little bit show you by combining that. So our example will be very complete on that. The column, let's say 4 meter 2 centimeter, and this one going to be 1 2 3 4. Okay, and what we have is the shear diagram, and what shear diagram this is going to be negative. Okay, and it's going to be minus 10.23 kilonewton, and it's also minus 10.23 here. Just put like this, and then you may say the slope here is 0. That is going to be the shear diagram, and then you have this one for 27.42. So this is 10, right? So scaling the is going to be 4 times of this. No, 2.7 times of this. This is 3. It's going to be 3 times 3. That is going to be about this. That is going to be plus 27.42 kilonewton. Get this. And then this is going to be minus 20.58. So it's going to be about this. That's it's going to be minus 20.58 kilonewton. And then you get this diagram, and you get the 0 here, and you got to put the slope here equal to minus 6. That is going to be the shear diagram. This is going to be the shear diagram of the frame. Okay, and if you like to draw the diagram for the moment, okay, let us put the column here and put the beam here. Okay, this is going to be the moment diagram, and it is up 13.56. This is up. Okay, and then this is plus 13.56 kilonewton meter, and then it's downward until here. The moment here is going to be 27.36. This is going to be about this. Okay, and the slope here is minus 10.23, and the value here is what? Minus 27.36 kilonewton meter. Okay, and then come here. This one also have the minus 27.36. That is going to be about this, and you may point this one, and the graph is going to be up to this one of about here is 35.34. So over here is S equal to 0, and this one is 35.34 kilonewton meter, and the graph gonna have the shape like this. Okay, it's going to curve up like this, and you also has the slope here. It's also have the value of minus 27.36, and it have slope. The S equal to 27.42, and it's up like this, and then it's also come down like this, and you got the moment here of 0, and you have the slope here equal to minus 20.58. Okay guys, it's important for us to highlight the slope, highlight the slope, highlight the slope, and highlight the slope. And also, if possible, you got to highlight the value of this, and this is 0. And for this, you may highlight this one for s equal to 0, s equal to minus 6, and then you highlight some important value here, also 0 here. Okay, that is the shear diagram and the bending moment diagram of our frame. Yeah, it took some time to dot it, and I hope you will be able to draw this kind of diagram. I recommend you guys to start by watching this, and then I also like you guys to do everything by yourself to practice it. Okay, that's the end of the clip.